Weak acids and strong bases. So the problem is the terminology that we use can sometimes be confusing. Strong acids and bases are listed because of the way that they have an effect on the pH of the system. So strong acids will dissociate completely. So what I will have here, for example, hydrochloric acid, is I'll have a single-headed arrow and H plus Cl minus. So when my strong acid is put into a solution, my initial concentration of my hydrochloric acid will equal my final concentration of H plus ions because it will dissociate completely. Weak acids, however, reach an equilibrium. They do not dissociate completely. HF is an example. So hydrofluoric acid, when it dissociates, there's a double-headed arrow to show that it reaches equilibrium. And so my initial hydrogen fluoride ion concentration will not equal my final hydrogen ion concentration because some of it will stay as HF. There are 6 strong acids that you have to know. It's HCl, HBr, HI. These are the halogens that don't include HF. And then HNO3, H2SO4, and HClO4. So hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. The strong bases, if you go down the alkali metal column, goes lithium hydroxide, potassium hydroxide, sodium hydroxide. Then you hang a right, and you get to calcium hydroxide, strontium hydroxide, and barium hydroxide. So these are the 6 strong acids and bases. You need to memorize those because here's the thing. Anything that's not a strong acid or a strong base will be weak. So strong refers to its ability to affect the pH. So strong acids will affect the pH more than the same concentration of weak acids. And weak acids will have a Ka with them. So if I look at a 0.5 molar concentration of HCl, it will dissociate completely. So if I put in 0.5 moles per liter of HCl, I will end up with 0.5 moles per liter of H plus ions. I can find the pH of that, and that will be 0.3, a very low number. The same concentration of HF, when it dissociates, I will have less than 0.5 moles per liter of H plus ions at equilibrium, so my pH will be higher than 0.3. So adding the same concentration, my pH lowers from 7 to 0.3, has a much stronger effect, whereas with HF, it won't go as low as 0.3. So a weak acid is weak because the anion holds on to the H plus ion and won't allow it to leave. So weak acids have a KEQ. So you can think of a weak acid as weak because it has a strong anion. The intermolecular force of attraction between the anion and the H plus ion is really strong. Water can't rip it apart. So weak acids have a KEQ. So acids have a Ka and bases have a Kb, weak bases. The lower the KEQ value, that means that you're not going to have as much product, which means that it's not going to dissociate as much. So the lower the KEQ, the weaker the acid or the base. The lower the Ka, the weaker the acid. And the weaker the acid, the less it's going to cause the pH to drop. The lower the Kb, the weaker the base, the less it's going to cause the pH to rise above 7. So here's an example where we actually are looking at numbers now. So Ka of HF at 25 degrees Celsius is 7.4 times 10 to the negative 4th. So if I'm looking for the actual pH of that 0.5 molar solution of HF that we just talked about, I can apply the Icebox Rule, and I can actually apply the 5% rule because 0.5 is at least 10 to the negative 3rd times greater than 7.4 times 10 to the negative 4th. We're close enough. So we're just going to apply the 5% rule. So I run it through my icebox. My Ka is equal to H plus times F minus over HF. These two are equal because they dissociate in a 1-to-1 ratio. And so when I solve for X, which is my H plus concentration, that ends up being 0.019 molar. And if I take the negative log of that, that becomes 1.72. So if I'm comparing again, my 0.5 molar HCl caused my solution to drop to a pH of 0.3, that same concentration of HF causes it to drop to 1.72. So again, it's weaker because the pH does not go down as much. So now let's look at bases. So the pH of a 0.5 molar solution of LiOH, which is a strong base, versus a 0.5 molar solution of NH3 that has a Kb that's equal to 1.8 times 10 to the negative fifth. So LiOH is a strong base, so it dissociates completely. So if I put in 0.5 moles per liter of lithium hydroxide, I will end up with 0.5 moles per liter of hydroxide ions. So the pOH is equal to the negative log of this, which is 0.3. And the pH is equal to 14 minus that, so my pH ends up being 13.7. That's an astonishingly high pH. If I'm looking at my Kb, and I'm looking at my 0.5 moles per liter of NH3, which is ammonia, I again run it through Icebox. This time it's clearly 10 to the third times less than 0.5, my initial, so I can safely assume the 5% rule. I run it through, my Kb is equal to my ammonium ion concentration times my hydroxide ion concentration over NH3. And that equals 1.8 times 10 to the negative fifth for the Kb. X is equal to my hydroxide ion concentration. So when I solve for X, I get 3 times 10 to the negative third moles per liter. My pOH, which will be the negative log of that, will be 2.5. And my pH will be 14 minus that pOH, which is 11.5. So again, if I'm looking at the difference, a 0.5 molar solution of lithium hydroxide will cause my, this should be 13.7, will cause my pH to increase to 13.7, whereas the pH of my 0.5 molar solution of ammonia would cause my pH to rise only to 11.5. So again, it's weaker because the pH doesn't rise as much. And finally, when you're looking at the relationship between Ka and Kb and Kw, Ka times Kb equals Kw, and that may not make as much sense. You think to yourself, well, isn't the base, if I'm looking at the conjugate base of something, just simply the reverse reaction? Why isn't Kb 1 over Ka? So it has to do with the fact that it's all in an aqueous situation. So with the acid, it's easy. I can just say it dissociates and forms an H plus ion and my anion. So my Ka is H plus times A minus over Ha. But my Kb, if I'm looking at my A minus acting as a base, my conjugate base, it's not going to just sort of take a random H plus ion. It's not simply the reverse reaction. What's happening is that I'm taking that A minus and I'm placing it in water. And what it's doing is it's ripping that H plus ion from H2O to create the HA and the OH minus ion. Because H2O has its own equilibrium system there, basically they're fighting. The OH minus ion is fighting the A minus ion. They both have a KEQ value. And that's going to change my actual Kb value. So another way of looking at it is if I look at my Kb expression here, it's going to be Ha times hydroxide ion concentration over my A minus concentration. Well, let's just happen to multiply the two of them together. So my Ka is this, right, from this expression up here, and my Kb is this. And lo and behold, when I multiply them, my HAs cancel out. My A minuses cancel out, so my weak acid and my conjugate base cancel out, and I'm left with H plus times OH minus, which is your Kw.